First of all, thank you very much for giving me the podium here to tell you a little bit about this topic of quantum communication and particularly networking, which is the futuristic vision of this talk. And so without further ado, let me begin. So first of all, I want to compare and contrast what we mean by quantum communication. And so classical communication consists of a sender, named here Alice, trying to communicate a classical bit string. And this is notionally represented here as a bit string. Could be the register of your PDA that everybody carries in their pocket. It could be the transmitter of a laser communication transceiver. But it's a string of ones and zeros which need to be communicated to a receiver named here Bob. And early in days, a voice call, digitized, or perhaps these days, data communication. Back in the 1940s, Claude Shannon showed that irrespective of this channel that connects Alice and Bob, there is always a possibility of error-free communication below a certain channel capacity. It took almost 40, 50 years to find the right kind of codes to do efficient error-free communication. Nevertheless, this kind of system is practiced ubiquitously today. And we all benefit from the connectivity that it provides. One can ask, can we do the same when this register actually is a quantum register, perhaps the output node of a quantum computer? And similarly, on Bob's side, there's another quantum machine as an input node of input to this quantum machine. And of course, this register then, these red dots are qubits, which are quantum states that could be in superposition, undergoing some processing that needs to be mapped over to another quantum processing device on the other end. And one can naively ask, is similar kind of a thing possible? And the moment you ponder over it for a minute, you find that there are conflicts with quantum mechanics. First of all, there's the no cloning theorem. In the usual case, in classical COM, you would have two copies of the same register, and that kind of a thing is prohibited in quantum mechanics. And you couldn't even measure and recreate because quantum mechanics disallows, the Heisenberg uncertainty principle disallows precise measurement of that state for recreation purposes. So it seemed like this was a no-win situation until in 1993, Bennett and co-workers found a way around this conundrum with conflict with quantum mechanics, and they proposed this so-called Teleportation Protocol. It requires a new resource. It requires what we call entanglement. So if Alice and Bob, for example, pre-share a pair of entangled bits labeled here psi TR, T for transmitter, R for receiver, and if Alice wants to send a qubit in that superposition state, the protocol says that she makes a joint measurement on her half of the entangled bit and the qubit that she wants to transmit. And upon the joint measurement, it's a 2-qubit measurement. So there's the outcome is one of 4 possible choices, 2 bits of classical information that she sends by some kind of a communication channel to Bob. And that allows Bob to turn his half of the entangled bit into a state that exactly is the state that Alice wanted to send. In the process, because the joint measurement she made, I think this thing is kind of dying. In the process, the joint measurement she made, she loses her qubit that she wanted. There's no trace of that qubit in her possession, and it appears at Bob. So this kind of a teleportation protocol underlies all of quantum communication that we think of today. Here, of course, I illustrated this in terms of for qubits. A similar protocol also exists for other continuous variable quantities or continuous variables in which one can describe the quantum field, which oftentimes is the amplitude and phase quadratures of a light wave that generally are modulated to send information. In this talk, I'm not going to touch much on this continuous variable quantum information just for the sake of not having enough time, but nevertheless, protocols for teleportation of continuous variables exist in the literature, have been demonstrated, and shown to work. So, as I've stated, how we envision quantum communication, that resource of entanglement needs to be everywhere. So Alice and Bob, if we are to do some kind of a networked quantum communication, we envision some kind of a network quantum communication network, then we need to have a ubiquitous presence of this entanglement among the users on the network. So this whole problem of quantum communication boils down to having this entanglement produced in copious amounts and distributed to various parties that are on the network. And not only you should produce copious amount of it, you should also, as it distributes, it should not degrade. So entanglement distribution network underlies this kind of a quantum network scenario that one envisions. So over the years, a lot of progress has been made, but there is a fundamental rate distance bottleneck. And to understand that, one looks back at the history of classical communications. And I know there are many students in this room, and many of them may not be familiar with the history of classical optical communication. And I've sort of listed here, won't go into the details here, but the important point here is that as you distribute this entanglement, there's necessarily loss because Alice and Bob are distributed over distance. Whether you do it over free space, then there is a loss due to diffraction unless you use very large optics. Or if you go through fiber, then there is that inherent 0.2 dB per kilometer loss. So going 50 kilometers already gives you 10 dB of attenuation. That means the rate goes down. And there are no devices in the quantum domain that can amplify signal, which played a big role in the development of this classical communication infrastructure that we envision today. That invention of the erbium amplifier more or less changed everything. It turned this exponential decay of signal to noise as you go through fibers into a linear loss because of the repeated loss and gain cycle that the amplifiers provided. Of course, in the quantum case, there are approaches. One is this quantum repeaters, which the community is looking for. No one has demonstrated yet. So I'm not going to talk much about it unless there is some time at the end to talk about this. But the approach that has been followed is this based on trusted satellites. So instead of linking users with fiber on the ground, you send information or you send your entanglement distribution source up in the satellite, and then because in that case most of the propagation is in free space, you can connect users that are thousands of kilometers apart with low loss channels. And this is the approach that the scientists in China have been following, and elsewhere in the world as well. So I want to highlight some progress that has occurred in this area before I talk about networking. So from here on, I'm going to talk about the entanglement sources that have been deployed, ruggedized, launched in space, and also in fiber networks. So there are two types of systems that people have built over the years. One are based on this SPDC, spontaneous parametric down conversion in Chi2 crystals, which can also be in the form of waveguides. And the second is this SFWM, or spontaneous full-wave mixing, which are based on the third-order Chi3 nonlinearity in fibers, or more recently in silicon photonic-type platforms in the form of ring resonators and mostly in, again, various portions of the optical spectrum. So I'm going to spend some time overviewing the progress and where we are in the context of quantum optical communication based on these devices. And there's the third one referred here, which I'm not going to talk about, which is based on atomic ensembles. One of the inherent drawbacks of many of these sources is that the entanglement is quite broadband. If you want to couple that to narrowband atomic memories, it becomes difficult to do that. But as I said, time is limited, so I probably won't talk much about this third bullet here. So again, this is just a sort of a review. These pictures are from some early work. They're only representative here. I'm not emphasizing anybody's work, and I will highlight some state-of-the-art work that's been done over the years. In spontaneous parametric down conversion, a light beam is focused into a Chi2 crystal. A pump photon interacting with the Chi2 nonlinearity splits into signal and idler daughter photons. So in this case, in spatially non-degenerate modes that are collected in optical fibers. In order to enhance the interaction or make it more efficient, one can guide this light into a waveguide, which is quasi-phase matched, so that one can use a higher nonlinearity to make this process efficient. And this kind of a system leads to a very efficient way of doing these kind of things. So an example of this is the entanglement source that was launched in this satellite Messias. So this source actually is slightly different. It was demonstrated back in 2006 in the group of Franco Wong at MIT. It is a very stable source based on type 2 spontaneous parametric down conversion in a polarization Sagnac loop. Essentially, use of the Sagnac loop in the polarization geometry makes this phase stable. So what happens is that a pump photon, as it enters, you diagonally polarize it or polarize it in some way so the intensities on the two sides are equal, but there could be a phase shift. And as the pump photon goes one way or the other, it is pumping this periodically poled KTP crystal. So depending on that spontaneous down conversion event occurred going clockwise or counterclockwise, the signal photon that, let's say, it's launched into this fiber is horizontally or vertically polarized. And since one doesn't know which direction it got created, you get an entanglement. In this case, polarization entanglement, which is very stable. The scientists in China, of course, ruggedized this kind of a system, space qualified it, and put it on the satellite. And in this particular case, this source sitting in the satellite produces about a mega pairs per second, which are then distributed by free space standard optical links to two places that are almost 1,200 kilometers apart, and they showed violation of Bell's inequality. So just to give you an idea, if you try to do this kind of a distribution of entanglement over 1,000 kilometers in standard optical fiber, you would get 200 dB of loss. In fact, nothing would make it across that channel. So this is an example of how ruggedized, how practical some of this technology has become. And more dramatic example of how good some of this stuff has gotten is this a CubeSat that was built at the National University of Singapore. And in this case, of course, their goal was just quantum key distribution, so it was not entanglement. So they had a type 1 collinear non-degenerate spontaneous parametric down conversion. And unfortunately, as this CubeSat, it's a very small package, ruggedized, as it was being launched, the rocket exploded. Of course, this package was destroyed, but they went ahead and recovered the actual source from the wreckage, and they showed that it survived that rocket explosion. So shown here is this before. The red is the before, blue is the after. So what they're showing is coincidences as they vary the polarization angle of this polarization shifter, liquid crystal-based device. Again, that also survived. It's amazing to see that the two of them, when the whole package worked together and almost reproduced the same effect that they had before. So what this tells us is that this technology has become well-packaged, space-qualified, ruggedized, and we can launch even in CubeSats. CubeSat launches, anybody can think about nowadays with $100,000, you can think about sending quantum payloads in space. So I think this is an amazing amount of progress. Moving on, so coming back to, again, a representative sample of the work with waveguides, and this is kind of a crowded diagram taken directly from this paper is on the archive recently from Christine Silberhorn group in Paderborn, Germany. What they did is essentially the same polarization setup, but instead of a bulk crystal, as in the satellite, they're using a periodically poled KTP waveguide in the Sagnac loop. What that does is it cleans up the spatial modes. And in fact, the metrics that they list here and compare with what is achievable with, so far in the past in a table that is in that paper, you get almost 90, not only you get the same very stable interference fringe, this 2-photon interference fringe indicating polarization entanglement, you get the very high fidelity as you do the 2-qubit tomography, 96 fidelity to a singlet state. If you prepare 2 entangled photons and detect one, and the 2 identical ones that remain show very high degree of Hongo-Mandel interference. This Klitchko efficiency, it's another metric. It's a ratio of the pair of photons that are down-converted in spontaneous down-conversion divided by the single counts. Usually, when you detect only the pairs, this Klitchko efficiency is quite small. In this case, it's almost approaching 50%. That means that every time you see a coincidence click, there is a single count there. And that's an important metric that determines the overall efficiency of devices like this. And they're very efficient. With milliwatt of pump power, they're creating about 3 mega pairs per second. So this kind of, so the technology in creating waveguides and ruggedizing that, although this is kind of on a tabletop, but potentially it could be ruggedized into a small form package. So that tells us what the state of the art is in Chi2-based entanglement sources. Moving on to, I'll talk a little bit about Chi3-based systems, and this is where most of my work had been focused in the last couple of decades. So back in the 90s, as that classical optical communication was taking place, I was interested in parametric amplifiers, particularly exploiting the Chi3 nonlinearity of fibers. And the reason was that in classical optical communication, the gain band was limited to the erbium bandwidth. So we had like 30, 40 nanometers of gain available around 1550 nanometers. And the question we were asking was, can we utilize the very broadband nonlinearity of fibers to have amplification that goes way beyond that band? And in fact, through the 90s, we did several experiments in which we made parametric amplifiers and parametric oscillators utilizing the Chi3 nonlinearity of standard fibers, although this work is for microstructure fibers that was provided to us back in Bell Labs in circa 2000. Similar results were obtained with standard fiber and dispersion-shifted fiber in this reference that was a parametric oscillator. So the moment you pump near the zero dispersion wavelength of the fiber, what you find is that you get these sidebands that appear, which people have called the modulation instability sidebands. And to me, it was a curious question that if light is originating here, eventually from vacuum, so there must be correlation in these photon pairs. So we launched an effort to do photon counting sitting very close to the pump wavelength in various kinds of fibers, in microstructure fibers, and dispersion-shifted fibers, standard telecom fibers. And I'll give you some examples. And we conclusively showed, first in this paper in Photonics Technology Letters in 2002, that one can create these signal-idler photon pairs. You can have non-classical correlations. In fact, one can convert that into polarization entanglement, and through a series of papers, we showed that the process is exactly identical to parametric down conversion, except that in parametric down conversion, a pump photon comes in and splits spontaneously into signal-idler photons. They could be degenerate, non-degenerate, and so forth, depending on the phase matching. The same holds. You have a 4-photon scattering process, 2 pump photons that could be identical, that could be different. They scatter through this Chi3 nonlinearity to create, in an energy-conserving way, signal and idler photons. And that could be degenerate as well as non-degenerate, could be polarization entangled, and so forth. So after establishing, and many other groups followed this kind of work in fibers, So here's an example of some work we did back in 2006. It was a post-deadline paper at OFC. Our goal was to try to put this kind of technology in systems almost more than a decade ago. So here was a source we built in as a dispersion-shifted fiber, which is pumped again by a diagonally polarized light for the sake of brevity. So depending on which direction, clockwise or counterclockwise, these signal idler photon pairs are generated through spontaneous full-wave mixing as they come out. And if you separate them, they are polarization entangled. The point here was that these things can coexist with standard classical communication. So this was the crux of this, this work that we presented at OFC, was to send these signal idler photon pairs on a defined quantum channel in the fiber, send one photon 50 kilometers to one side, another photon 50 kilometers to the other side, while these 50-kilometer spools of fiber carried classical communication traffic on different wavelength bands. And by use of WDM filters, we were able to extract these polarization entangled photons and show that there was high two-photon interference visibility after 100 kilometers of signal idler propagation. So this showed that, yes, you can put entanglement, in this case generated directly in the fiber. It can coexist with classical traffic. Of course, there's contamination that comes from mostly Raman scattering that these signals, classical signals do. So we had to attenuate this classical traffic to a reasonable power level. So it's minus 10 dBm, which is about a 10 dB lower than a classical channel may have. So other than that, it was these standard 10 gigabit per second channels. So this showed that this kind of entanglement can be put into practical use. And since then, and I'll come back to this, we built another source based on standard fiber in the telecom O-band. Again, because of Raman scattering, and I'll come to the justification of this in a few minutes. By use of a double pass setup in which the pump light comes in, again diagonally polarized, goes through a polarization dependent delay. But now, doing a double pass through a piece of standard SMF28 fiber, which is dipped in liquid nitrogen to reduce this Raman scattering, we were able to create a very, very stable source of polarization entangled light with a fidelity almost approaching 100% in this case because of cooling of this fiber. And this kind of a system can be very rugged. You can turn this on and off, and this is test of one of those that was described in this paper, running over days. You can turn things on and off, and the fidelity to the initial entangled state remains. And the goal of this was in switching, and I'll come back to this later, use of this source and other. Also, it is important in a quantum communication network that if you generate photon pairs, then different sources generate them so then the two sources are identical to each other. And this kind of a work had been done with high sapphire lasers, but not in the communication channel. So what is shown here are demonstration that you can actually use telecom band components, create signal idler photon pairs, the photons of which are identical if you pump them with separate lasers. So in order to demonstrate that, we had a CW mode-locked laser that was running at 10 gigahertz rep rate. But this laser has a finite coherence length. In other words, if you look at successive pulses coming out of it, after a certain amount, these pulses lose phase coherence with the previous pulse. And that's the first order coherence that people talk about. So we use this kind of a laser to pump two identical spontaneous full-wave mixing sources, put an extra fiber in its path so that if this fiber is pumped by one pulse, this fiber is pumped by a pulse that's successively further down. And further down so that there's no first-order coherence. So that means that these two fibers are as if they are being pumped by independent sources. And then bring those two pairs, detect one, herald signal photons, and do Hongo-Mandel interference. And what we were able to show is that as you change the length of the fiber, you go to successive delays. So here's the first order interference visibility in successive pulses. After 100 or so pulses, so each pulse 10 gigahertz rays about 20 centimeters apart, you don't have any coherence in the pump that creates those signal idler photon pairs. But the Hongo-Mandel interference visibility as you go remains more or less identical. So this key concept was utilized then in this experiment in 2016, again led by John Wei Pan's group, where they created a model network. And I'll come back to the networking applications in a minute, where they created and here's the detail. So the Charlie in the middle distributes entanglement to two parties, Alice and Bob, and then Alice teleports the qubit that's created again through spontaneous full-wave mixing in this dispersion-shifted fiber, and another dispersion-shifted fiber that creates the pair and goes to the two sides. Again, it relies on the fact that if you use the right type of WDM components, the photons that are scattered pumped by independent lasers actually show that identical photon behavior that can be used to do teleportation. So this also shows that this kind of sources have become very, very, very practical. I want to come back and talk a little bit about Chi-3 and silicon photonic type platforms. And this has proliferated actually quite a bit, so I will not be doing justice to all the groups that are working in this field, except to highlight a few things. Of course, this initial work on this was also done in collaboration with Mikhail Lipson and Alex Gaither's group. The history is that Jay Sharping, who had just graduated from my group doing these fiber experiments, became a postdoc with Alex Gaither, and that's exactly when they were creating these nanophotonic silicon waveguides in which modal dispersion and material dispersion were compensated to achieve phase matching to get full-wave mixing. And the moment Jay saw this and we talked and we realized that yes, it can be used to do photon pair generation, very similar to what we'd done in fibers. And within a few weeks, they brought the device to our lab, same exact device that was used in their Nature paper we used to get these photon pairs to show that, yes, indeed, you can have signal idler photon pairs that show high coincidence. And some of the data from that paper is listed here. This way of doing photon pair generation is important because now you can think about doing very, very compact chip scale sources. And as I said, this has proliferated into too many groups for me to review here. I want to bring to your attention one paper that just recently came out in Nature. It creates topological edge states in these microring structures and utilizes spontaneous full-wave mixing in these edge states that are stable to imperfections in fabrication of these devices. And they were able to show the creation of signal idler photon pairs if they pump in this clockwise edge, that light going through this way, and showed that you can get a decent coincidence to accidental ratio and this G2 that dips below 1 when you look at the same pulses. And also they simulated the similarity, that is, if they didn't use these edge states as the number of rings increases, if they didn't use the edge states like in a linear chain, the similarity factor goes down, but in the edge states it remains high. So this is an interesting development for potentially future technology in which you can tolerate imperfections. But to me, that's great, but there is an underlying challenge that still needs to be worked out in this compact sources, and that has to do with light scattering that is due to the pump. So for example, in this experiment, and in fact, if you look at many of the other experiments, a similar thing holds. You have to heavily filter the output. And typically, 100 dB of filtering is required because, just give rough numbers, it takes about 10 to the 7 pump photons per mode to do this four-way mixing, spontaneous four-way mixing, given the nonlinearity. And you're creating spontaneous. That means that your probability of scattering is a few percent. Otherwise, you have multi-pairs, and that degrade entanglement properties. So that means that if you're at a few percent level with 10 to the 7 photons, you have 10 to the minus 9 probability of creating a pair. And if you want to have a decent signal-to-noise ratio, you need 100 dB suppression of those pump photons in these kind of systems. And that's why you need this very heavy filtering. And in most of the work that has gone on in integration of these kind of devices on a chip scale and scaling this thing, all the filtering is done off-chip. And that's, to me, that's a big drawback. That problem needs to be solved for these kind of things to become usable. And there are attempts in doing that, and I want to highlight one. This is some work came out of Milos Popovic's group, originally done at University of Colorado in Boulder, but now at BU. They were able to integrate not only the generation rings, but also filtering rings on chip. And then the light that is scattered out, this is a CMOS process, and they have structures in which whatever the pump light is scattered out is reabsorbed, and it can't re-enter the waveguides to give contamination at the output. So this, although still more work needs to be done, here's the 2-photon interference visibility and on-chip selectivity in terms of suppressing the pump. A lot more work needs to be done before one can have a small form package like the one we have in classical communication. You want to have a package in which pump light in, I mean, let's say the laser is not integrated on board. We can have a separate laser. You go on the chip, and 2 fibers bringing signal idlers out. And I think that is still a challenge because of this very mundane filtering requirements and so forth. But there's a tremendous progress being made. OK, so I don't know how I'm doing on time, Peter.
About 10 minutes full.
OK. So I want to move to a little bit of this futuristic side of things. So what I've given you is a glimpse of what kind of quantum communications has been done in free space, satellite space environment, as well as in terrestrial environments in the fiber. And there was this, so I want to move to this networking side of things, where we are and what can we envision in the future. Although this vision is maybe 20 years further ahead. But as they say, predicting future is almost impossible. You're always going to be wrong. So take that with a grain of salt. Kimball, back about a decade ago in 2008, envisioned a quantum network. These are nodes connected through quantum channels. And of course, they had a way to store qubit in these atomic states that could be read out by means of a guiding pulse. So deterministically, a photon could be launched into the fiber, and then by having a conjugated pulse, it could go back into the system. And some rudimentary demonstrations of this kind have been done. But recently, there's a tremendous uptake in quantum computer technology. So the vision now is that because of the tremendous progress in quantum computing, one needs to envision some kind of a heterogeneous network in which you may have quantum machines based on ions, on superconductors, on atoms, perhaps even photon-based quantum processors that need to interconnect with each other. And of course, depending on the architecture, you also need some kind of a routing function. And so it is in this context that I want to talk a little bit about what the challenges remain, what progress is being made. And my personal work over the last, before I went to DARPA, had been on this quantum router side. That how do you steer entangled photons that could be entangled with some other entity that you may hold, but you can steer it to different nodes while maintaining that entanglement. So I want to talk a little bit about this quantum switching. And here, let me differentiate what I mean by quantum switch. So you have a device in which the inputs, and these could be 2 qubits, for example, A to C, B to D, but you have some kind of a control that switches them while preserving whatever entanglement they may have among themselves or with something else in the world. And of course, one should have desirable features. It should have high contrast, low pump threshold. More importantly for quantum signals, very low loss as they switch or go across. And then they should, of course, preserve this quantum state information. If the switch happens to be also quantum mechanical, then that's your C0 gate or a Fredkin gate. But here we're talking about the switch that could be classical. We want to route quantum information in some kind of a network. So pump could be, in most works, it'll be classical. And we designed a cross-phase modulation-based switch that has all the characteristics that are needed, and that could be very versatile. And of course, it's based, initial demonstration is based on fiber. One can envision chip-scale devices, just like in the case of photon pair sources. And it's the details are, in some of the papers I'll cite, you have some kind of an interferometer, in our case here, a Sagnac loop again, and you couple in a pump light that travels around and has some kind of a group velocity mismatch with the signal that's coming in. What that does is it has this pump walk through the switching window so that each point of your wave function of the photon that's coming in sees the same cross-phase modulation phase shift. So if you do that right, and in our case, this pump had to be very carefully designed. If you do that, you get almost like this line switch. Depending on the pump being on and off, you can direct things, or you can do superposition. You can have a superposition state coming out, and which, of course, in the classical case, will lead to disaster. And we implemented this, and this is where we had to create that O-band source that I described to you before. The requirements of pi switching are much more stringent than a very small amount of scattering probability when you do spontaneous full-wave mixing. So that leads to a very strong Raman scattering, and we needed a source that would sit way far on the anti-Stokes side and will be Raman scattering free. And so we built that. So here is that polarization entanglement device in the O-band that I showed you before. And we integrated that with the switch, and these are a few fiber components. And here's a characteristic switching window. So because of the group velocity mismatch between the O-band and the C-band, the switching window is like 2 picosecond per meter of fiber that's used. So in this case, depending, there's a 100-meter fiber, so about 200 picosecond window and about 850 picosecond window. And the contrast is actually very good because these pulses walk through each other. And here's the fidelity with the pump on and with the pump off, and you can see there's hardly any difference. So it leads to very good switching. And this fidelity is between the signal photon that is switched and the idler photon that's kept. So when the pump is, when the passive state of the switch and the active state of the switch, the fidelity is a measure of the degradation that occurs then in the switch, and there's hardly any degradation. And we use this to do a switching and routing function. So for example, in the end, these photons are detected with detectors which have a detection window of about a nanosecond or certainly much longer than the duration here that the pump pulses can separate. So we defined 2 quantum channels, about 300 picoseconds apart, and each time slot we created a different quantum state. So psi 1 here is, let's say, HH plus VV state, and its tomography here. Psi 2 is this HH minus VV state with the phases of these octagonal terms reversed. And of course, this forms an incoherent mixture if you detect the two together, and you get an entanglement fidelity that looks pretty bad. It's an incoherent mixture of the 2 time slots. But now, so this is what I showed you just now. Now if you can use your switch to separate out one of these time slots, because the switch uses a short pulse, so it can redirect one of these time slots to another channel. And you can separate out these two, and then when you do the tomography, and you recover a very high fidelity. So this demonstrates that you can create quantum channels. You can time division multiplex, and there are other ways, and people are talking about wavelength division multiplexing, or these kind of states in different degrees of description of the quantum field. But nevertheless, you can build routing functions based on these kind of devices. OK, so I want to come back. Thank you. I want to come back to this picture again. Can we envision, now that there are some examples of quantum routers, and there are these other kinds of quantum machines that are coming online, can we really envision this kind of a network? And this is the speculative, or you may want to call it a visionary talk. And as I said, it could be all wrong. So the point is that quantum networking, is there a case? And I think there is a case, although it's a question mark. And for nothing else, the history shows that we will be led into looking into this. And that is because there are several groups building quantum machines. So this so-called noisy intermediate scale quantum, or NISQ technology, is already here. With all these companies, they will want to sell quantum machines. How large they will be in terms of how many qubits they can process. Clearly, they will not be logical qubits. These are physical qubits, 20, 30, 40, 50, one can envision. But once they build one, they want to build many. If you build many, people would want to interconnect them together. This situation is no different than what was in the 60s and 70s. If visionaries like Vint Cerf didn't want to connect very, very small machines, 4-qubit, 8-qubit machines, to talk to each other, to do advanced applications, email at the time, we wouldn't be where we are today. So we have to think about networking for the very simple reason of distributed computing, for example. Can I take n-qubit machines, these logical qubits, if I connect them together, clearly not with classical communication, but with quantum communication, not full connectivity, but there's a huge gap between m times 2 to the n versus 2 to the mn. What kind of algorithm? How can I parse these things? Can I have applications in which the algorithm divides the quantum computation in appropriate ways to take advantage of the connectivity I have? So there's a lot of work that potentially can go on both on the theoretical side and, of course, in the connectivity, and try to put rudimentary test beds together of this kind. So I think this work has to start now. Otherwise, the same situation that existed if we had waited for classical networking till actually better machines came around, it would have been too late. Of course, there are lots and lots of technical challenges, and I've listed a few. All the entanglement sources I showed you, they are probabilistic. We need to have technologies for deterministic, and there are some proof of concept experiments. And again, I have not listed, apologize to those people, but there are some very nice proof of concept experiments out there. Quantum interfaces. In this kind of a heterogeneous network that I described, if I have a superconductor in which qubit information resides in the microwave, that needs to be converted to the telecom band, and that's a very challenging task. So this is what I've labeled as sort of quantum interface. You want to map stationary quantum states that may be in the quantum memory into flying qubits without loss of quantum information. That's the key part. Mapping quantum states from one wavelength to the other. This was some work that I had done in the context of squeeze state light long ago, which I'd called quantum frequency conversion, but that can be now generalized, where this quantum information resides in photons, in phonons, in mechanical modes, or microwave, or anything else. Similar concepts apply, and of course, switching, routing, multiplexing, demultiplexing, format conversion, I referred to frequency bin, time bin, polarization, and so forth. And I haven't had time to talk about repeaters, because yes, satellites is one way to overcome that limit. Giving trust to the satellite in a QKD scenario may be okay, But in this kind of a network quantum communication, we do need to have some kind of a repeater technology if we want to connect things that are further than just short distance apart. And of course, a lot of work, actually not a lot, some work going on in continuous variable, notably Kira Furusawa in Tokyo and Olivier Pfister in the US at University of Virginia. But this kind of a technology is not as far along as some of these qubit-based technologies. Finally, yet more technical challenges. If we build, how are we going to operate and control? So these are my random thoughts. How would we architect the quantum internet? Would it have a layered structure like the classical network? How would those layers be determined? Would entanglement distribution be a separate layer? How would quantum channels and classical channels coexist? After all, classical communication is an integral part. Teleportation requires classical communication. How would we control and operationalize it? How to share quantum channels among users? What's the best way to distribute entanglement to various users? Would there be entanglement factories that users can subscribe to? Would there be quantum ISPs? What about the quality of service? How would we measure it? What about software and algorithms to manage this quantum network? And of course, there are dots here, and these are just random thoughts. There are lots of other things that need to play. And I want to point to this DOE workshop next week, actually, in Rockville, Maryland, which will talk about many of these issues, quantum networks for open science, that I want to alert you to. Thank you.